So now we will be asking some other questions. How do we know what ocean pH was in the past? So then only we know whether there is a change or not. So without knowing what is the past values, we cannot say as of today what is happening, we cannot say unless we know what is the past. So direct methods are not possible because we cannot go back in time to see that what was the pH at that time. So we have to use some other methods by which we can actually know what could have been the pH earlier. So it is possible to calculate the ocean pH using CO2 concentration of air bubbles trapped in glaciers. So according to Henry's law, we can find it out. So during the ice sheet formation, so this is one way of finding it out, what was the pH back then. Or paleoceanographers use other proxies such as chemical and isotopic composition of fossil carbonate shells. So when we look at the natural carbon and the biogenic carbon, so the carbon that is present in the atmosphere, the carbon that is present in lithosphere, there is a difference in the carbon's isotopic ratio. So from that we can find it out what is the origin of this particular carbon, and from this we can also find out what is the ocean pH. Then uptake of boron. See, this is another important thing because boron is another important element which is involved in the study of ocean's acidification, especially dissolution of carbon dioxide in sea waters. So this uptake of boron and its isotopes into foraminifer shells, especially the microplankton that produce calcite shells, and the coral skeletons are indicators of the past seawater pH. So there is another way by which we can figure it out, because the relative abundance of the two dissolved species of boron in seawater, mainly the boric acid and borate, depend on the seawater pH. And because the relative abundance of boric acid increases at lower pH. In other words, the borate gets hydrolyzed to form boric acid at lower pH or under acidic conditions. So this is what is the overall process. So the marine carbonates incarbonate relatively less boron and with a lower isotopic composition under low pH conditions. So with this we can easily figure it out. If the boron is less, the pH was less. If the boron is more, then the pH was more. So other proxies for marine carbonate chemistry include uranium and carbon ratios, and in shells of benthic foraminifers also zinc and calcium and cadmium and calcium ratios. So these are all the other proxies. But what is the limitation in using all these proxies? See, the presence or absence of calcifying marine organisms in the geological record is not a good indicator of ocean acidification. The reason is the absence of carbonaceous remnants at the sea floor does not necessarily mean that the organism did not live in the surface, especially calcifying planktonic organism, for example, or even the deep ocean. So we don't know if something doesn't exist does not mean that it didn't exist. So that is the biggest problem. Something doesn't exist as of today. So that is the only thing we know. From that only we are going to find out what had happened earlier. So since the species doesn't exist now, we don't know whether it actually existed or it didn't exist. We have no idea. So that's the reason these proxies, existence of these proxies or non-existence of these proxies is a very tricky thing to use as a measure of finding out the ocean pH at earlier stages. And there is also some misconception related to the pH and the ocean acidification. The main thing is, see, the change in the hydrogen ion concentration is generally expressed as pH, which is a measure of acidity scale. So only for the acidity scale we are actually using it. And this is not acidity per se. That means it is not the actual acidity. It is only the scale in which we are actually using. So it does not measure the concentration of an acid, because when we talk about hydrogen ion concentration, we are only talking about a relative term. We are not finding it out like a hydrochloric acid or nitric acid or any specific acid we are not talking about. So that is the difference. And then higher pH means alkaline solution. So that does not relate to concentration of bases, because when we say higher pH, the ocean pH is around 8.2 or 8.1 when we say, it is actually in the alkaline condition. So that means these are not actually bases. There the hydrogen ion concentrations are lower. So that is the only thing. So we cannot say if a solution is basic, that means it is always having bases. So because that old Arrhenius theory and other things are not applicable, so that is what is a misconception we have to understand. Then of course another important parameter what we are talking about is ocean acidification. So ocean acidification means the pH should be below 7. So this is a simple misconception we will have, but unfortunately the pH changed from 8.2 to 8.1. That is what we call as a ocean acidification. Ocean acidification does not mean or does not refer that the pH of the saline water, that is the ocean water, is below 7 pH. It is still in the alkaline region, that is 8.1 is the region that is happening. But compared to 8.2, 8.1 is slightly acidic in nature. So that is what we are talking about. Ocean acidification means instead of 8.2, which was earlier existing, now it is 8.1. So that is 0.1 pH difference happen throughout the world. See, the main thing is, even though we say 0.1 pH is not a very big number, so why do we have to worry about that? But unfortunately, this is not for a small 1 liter flask or something we are talking about. We are talking about the entire world. So the ocean change, if it happens 0.1 throughout the entire globe, that is a huge difference. The pH is a hydrogen ion concentration expressed in basically a logarithmic scale. So the change in 1 unit of log scale represents change in H plus ions 10 times in the normal scale. So this is what we had seen. So from 8.2 to 8.1, when we go down in the pH, what actually happens is 26% of H plus ions concentration actually changes. So that is what is the actual things happening. And what is the difference between pH change and H plus ion? So if you say that 8.2 to 8.1, the difference is only 0.1 pH. 7.5 to 7.4, there also the difference is only 0.1 H. So when the pH changes from 8.2 to 8.1, the amount of hydrogen ion that is changing is entirely different when the pH changes from 7.5 to 7.4. In other words, the hydrogen ion concentration at 8.2 has a particular value. Similarly, the hydrogen ion concentration at 7.5 itself is a very different value. So the 0.1 difference and the amount of H plus ion difference are not related to each other. They are quite different. So what we have to remember is, if the starting pH is different, then obviously the amount of or the concentration of H plus ions which are going to change is going to be drastically different. For example, here is a simple example. So we have a 7.8 to 7.6 pH difference, that is 0.2 pH difference is the one we are talking about now. Now here the hydrogen ion concentration, if you look at it, is 1.5 into 10 to the power minus 8 at 7.8 and 2.5 into 10 to the power minus 8 at 7.6. So that means the difference between these two pH and the hydrogen ion concentration is 1.0 into 10 to the power minus 8 only. But if we go to a little acidic pH, say for example the difference between 4.7 to 4.5, still the difference between these two pH is 0.2 only. So the difference in pH remains the same, but when we talk about the hydrogen ion concentration, there is a drastic change. At 4.7, the hydrogen ion concentration is 2.0 into 10 to the power minus 5, and at 4.5, the hydrogen ion concentration is 3.1 into 10 to the power minus 5. So that means the difference between these two is 1.1 into 10 to the power minus 5. So if you look at these two numbers, then you obviously know that there is a 1000 times difference in the hydrogen ion concentration. So this is the major difference. So the very reason why we are having these numbers are hydrogen ion concentration, when we talk about pH scale, is basically in a negative logarithmic scale. So that is the difference. And there is another important thing, because we are talking about ocean. Ocean means it's basically marine science. So the normal chemist or the normal scientist, how do they measure or how do they understand pH? And the marine chemist, or the people who work in the marine science areas, how do they measure and interpret pH are little bit different. So that's what we are going to see. In the marine chemistry, people use total hydrogen ion concentration. So what do you mean by total hydrogen ion concentration? This includes sulfate ions. So basically when we talk about hydrogen ion concentration, we are not just talking about H plus ions alone. Here marine science people, when they talk about, they also include sulfate ions. So we will see why the reason. And if the same marine science talks about the physiological systems, they use free hydrogen ion concentration. So this is the major difference. Now we will see what are all these individual ions which we are talking about. See, basically the seawater is a very dilute bicarbonate solution whose concentration is 2 millimole per kilogram of bicarbonate is dissolved basically in some salt water. So this is what is basically the seawater we are talking about. So what are the major components of inorganic carbon that is present in the seawater? It has around 90% of bicarbonate anion. So that's why it is called as a dilute bicarbonate solution. And again, out of the whole 3 major species which exist, because when the CO2 dissolves in water, is carbonic acid, bicarbonate, and we also talked about carbonate anions. So these 3 species, CO2 in the aqueous form, bicarbonate anion, carbonate anion. The major portion is basically the bicarbonate anion followed by carbonate anion. Then we have only a very minute amount of carbon dioxide in the dissolved form, which is carbonic acid. So the pH of a particular sample of seawater depends on its temperature and pressure. So this is also another important factor we have to keep in mind. There are 3 major acid-base reactions which are happening in the seawater. So one is the carbonate system where CO2, bicarbonate and the carbonate anions are present. That is one system. Another one is the borate system where boric acid and borate anions are present. So that is the second one. The third one is the water system where we have water, H plus ions and OH minus ions. So the modern definition of pH actually uses, so far we have been talking about the H plus ions concentration when we talk about the pH, but the modern definition according to IUPAC talks about a little bit different terminology, which is called the hydrogen ion activity, which is written as AH. In aqueous solution, that is, it includes interionic forces when treating electromotive force data. So this is how the basic definition, pH is equal to minus log to the base 10 of activity of hydrogen ion. So it is not the H plus ion, but it is the activity of the hydrogen ion. That is what is given. So the activity is basically defined by the gamma H, which is the activity coefficient of H plus ions at molality mH, and standard molality is 1 mole of per kilogram of water. This is the standard molality. So this is how we are actually measuring the hydrogen ion activity and not just hydrogen ion concentration. That is the latest current definition by IUPAC. So there are different scales are used for the pH measurement. One is based on the calibration standards from the National Bureau of Standards or NBS standards. The other one is they try to realize pH as a concentration of hydrogen ion, which is what we have been discussing so far, and this is usually expressed in terms of moles per kilogram and not moles per liter. So pH in the marine science, when we continue, we know that for a given pH change, delta pH, the associated H plus ions change varies depending on the initial H plus ion concentration. So this is what we had seen. If it is 7.5, it will have a particular H plus ion concentration as the initial hydrogen ion concentration. So that is what is a very crucial factor for our studies. Let us consider pH2 is equal to pH1 plus delta pH, and in this relationship, some of the parameters we can actually rewrite as a we take this pH to the left hand side, then the delta pH equal to pH2 minus pH1, which is nothing but minus logarithm 10 to the power base concentration of hydrogen ions at condition 2 plus, because minus of minus becomes plus, so that is the reason the sign becomes changed, plus here log 10 to the power log to the base 10 of hydrogen ion concentration at pH 1, that is the initial pH. So this is how we can actually write this, and then when we rearrange that, we can write this particular equation. So we know delta H plus is equal to H2 ion concentration of hydrogen ions at 0.2 minus hydrogen ion concentration at 0.1. So when we substitute this value for the delta H plus ion, then we can find it out is the difference in the hydrogen ion concentration is basically the initial concentration into 10 to the power minus the difference in the pH minus 1. So this is how we can actually calculate what is the hydrogen ion concentration at the second level. So the equation 1 basically shows the change in the pH with reflect a relative change in the hydrogen ion concentration. But the equation 2 actually says that the same pH can equate to different hydrogen ion concentration changes when implemented at different initial H plus values. So that means even though we want to use a different scale, then we can actually use this one, whatever may be the starting pH, we can use the equation 2 for finding out what is the pH at another point.